Hey everyone, in this video we're going to go over section 3.1, derivatives of polynomials and exponential functions. Up until now we've been largely concerned with understanding what a derivative is. Now we're going to shift gears and discuss different techniques for calculating the derivative of a function. So let's begin. We'll start off with the derivative of a constant function. So for the derivative of a constant function, let's assume that we've got some function, f of x, that's equal to a constant. And if we apply the limit definition, f prime of x is going to be equal to the limit, as h goes off to 0, of f of x plus h minus f of x all over h. Well, for this function, f of x is always equal to c. So this is equal to the limit, as h goes off to 0, of c minus c over h, which is equal to the limit, as h goes off to 0, c take away c is equal to 0. 0 divided by h is 0, and the limit as h goes to 0 of 0 is equal to 0. So our first theorem, our first tool as I would call it, is that the derivative with regards to x of any constant is equal to 0. So by that, that's saying that the derivative with regards to x of 3 is equal to 0, or the derivative with regards to x of negative 2 is equal to 0. The derivative with regards to x of 1000 is equal to 0. The derivative of any real number, or I should, not real number, the derivative of any constant is equal to 0. Okay. So now we're going to go over the power rule. What the power rule says is that for any function f of x that is equal to x to the n, the derivative with regards to x of x to the n is equal to n times x to the n minus 1. So, we will do a proof of this. So let's prove this rule. We'll prove the power function. This will be our proof. By a proof, I'm going to show you why we know this. I'm not going to ask you to demonstrate proofs. I'm not going to ask you to give me proofs, or I might ask you to perform a simple proof. But I'm not going to ask you to recreate what I'm about to write. This is just for your understanding. How do we know this? So f of x is equal to x to the n. So by the definition of a derivative, f prime of x is equal to the limit, as h goes off to 0, of f of x plus h minus f of x all over h. Or, with this polynomial, we have the limit, as h goes off to 0, of x plus h to the n minus x to the n all over h. Now we're going to have to expand x plus h to the n. What we're going to do is we're going to use the binomial theorem. And what the binomial theorem says is that x plus h to the n is going to be equal to the sum from k equals 0 to n of n choose k times x to the n minus k, h to the k. And as a refresher, n choose k is equal to n factorial divided by k factorial times n minus k factorial. We're going to use these right here. So by substitution, this is going to be equal to the limit, as h goes off to 0, of, and I'm going to expand out the first couple terms of this binomial theorem. So this will give us n choose 0 of x to the n plus n choose 1 x to the n minus 1 times h plus n choose 2 x to the n minus 2 h squared plus we need n choose n minus 1 x to the 1 h to the n minus 1 and then plus n choose n of h to the n, and then finally we need this minus x to the n floating around on the end. Got a little long. All this is going to be divided by h. And so now we're going to expand some of these and we're going to do some simplification. This is going to be equal to the limit as h goes off to 0. N choose 0 is equal to 1, so we get x to the n plus n choose 1 is equal to n, x to the n minus 1 h plus n choose 2 is equal to n times, and I want to make sure, n minus 1 all over 2 x to the n minus 2 h squared plus some ellipses plus n choose n minus 1 is also equal to just an n x, I'm not going to write to the 1, h to the n minus 1, n choose n is equal to 1 plus h to the n minus x to the n. That's that minus x to the n that was floating around on the back. That's that minus x to the n from the beginning. All over h. Now we'll do some simplification. The only thing that's left, well, remember, we're taking the derivative of a polynomial. If you're using the limit definition to take the derivative of a polynomial, all of the terms in your original polynomial should get canceled out at this step. We've got an x to the n, we've got a positive x to the n over here, we got a negative x to the n over here. That's all the simplification we can do. Last couple steps. We'll just rewrite what we have. Limit h goes to 0 n x to the n minus 1 h plus n times n minus 1 over 2 x to the n minus 2 h squared plus some ellipses plus n x h to the n minus 1 plus h to the n, all divided by h. At this step, I would factor an h out of the numerator and cancel it with the denominator, but I want all this to fit in the remaining amount of space. So I'm going to use this h to cancel out with that h. It'll cancel out with one of these h's. It'll cancel out with one h from every term in the middle, and it will cancel out with one of these h's and one of these h's. So what we get is equal to the limit as h goes off to 0 of n x to the n minus 1 plus n times n minus 1 divided by 2 x to the n minus 2 h plus some ellipses plus n x h to the n minus 2 plus h to the n minus 1. And as h goes to 0, all of these terms are going to have an h in it. So that term's going to go to 0. Everything in those ellipses are going to go to 0. And these last two terms are going to go to 0. After h goes to 0, all that we're left with is n times x to the n minus 1. Combining what we have here with here, that shows that if f of x is equal to x to the n, then f prime of x is equal to n x to the n minus 1. So this is awesome. You're fine. How can we go about using this? So, with our power rule, and we don't need the theorem anymore, with our power rule, the derivative with regards to x of x squared, 1 minute, the derivative of x squared, well, n is equal to 2, is going to be equal to n times x to the n minus 1, or 2x. The derivative with regards to x of, let's say, x cubed, well, n is equal to 3. So that's equal to 3x to the 3 minus 1, which is 3x to the 2. If we wanted to take the derivative with regards to x of x to the 6th, that'd be equal to 6x to the 5th. The derivative with regards to x of x to the 11th is equal to 11x to the 10th. The derivative with regards to x of x to the 1000 is equal to 1000x to the 999. The power drops down, and our new exponent gets one taken from it. Nx to the n minus 1. Okay, so what else do we get? Perfect. So let's keep on going. This is all the same stuff. So on your guys' homework, problem 65 is actually to use the limit definition to show that the derivative with regards to x of 1 over x is equal to negative 1 over x squared. But if we write these with negative exponents, and it's common to do that in calculus, what that says is the derivative with regards to x of x to the negative 1 is equal to negative 1 times x to the negative 2. And the pattern holds. Back in 2.8, we actually showed that, and this is from 2.8, we showed that the derivative with regards to x of the square root of x was equal to 1 over 2 square roots of x. Or, written with exponents, we showed that the derivative with regards to x of x to the 1/2 is equal to 1/2 of x to the negative 1/2. So the pattern still holds. And in fact, and we'll show this later when we unlock the necessary tools to do so. We will actually show that the power rule, the general version of the power rule, RULE, says that for any real number c, for any real number n, not c, I'm sorry, I skipped ahead. For any real number n, comma, the derivative with regards to x of x to the n is equal to n x to the n minus 1. So that means the derivative with regards to x of 1 over x squared, when you go to take the derivative, like I said, in calculus it's typically much easier to work with negative exponents than it is with fractions, because we're going to develop a lot of little tools that look like this. So take your derivative and rewrite everything with without fractions. That would be the derivative with regards to x of 1 divided by x squared is the same as x squared to the, x to the negative 2. I'll write that again. The derivative with regards to x of x to the negative 2. Well, now applying our power rule, this is going to be equal to negative 2x to the negative 3. Negative 2 take away 1 is negative 3. Similarly, the derivative with regards to x of the cubed root of x squared. Once again, write everything with just exponents. Don't have any roots, don't have any division. Contain all the information that you need in the exponent. So, this is the same as x to the 2/3, which, applying our general version of the power rule, need a d, dx, because the derivative of this is equal to the derivative of this, which is equal to 2/3 x to the negative 2/3. And that kind of looks like a minus sign floating around, so I'll say is equal to the derivative with regards to x of x to the 2/3, which is equal to 2/3 x to the negative 2/3. So for this one, just as a refresher, if you guys haven't seen it for a while, that if you have the, I'll say the 8th root of x to the b, that's equal x to the b over a. You guys, if you don't remember that, it's fine, but you will use this a lot. Also, 1 over x to the n is equal to x to the negative n. These are two kind of algebra rules. Depending on when the last time you were in a math class, you might remember them or not. So, cool. So the power, I'll read this. The power rule enables us to find tangent lines without having to resort to using the limit definition of a derivative, which is awesome. Because if you guys, and I want to make sure, because you guys don't want to have to go through this every time. Chapter 3 is about quickly coming up with derivatives. You guys want to use just this information. This also enables us to find, it doesn't necessarily enable us to, it gives us an easier way of finding what some people call normal lines, which I believe largely just gets introduced as a talking point here. We'll do an example with one in a moment. But what a normal line is if I have some curve, and if we calculate the slope of the tangent line, or if we find the equation of the tangent line at a point, this is our tangent line. This is well, if we call this A, this would be the line y minus f of A is equal to f prime of A times x minus a, the equation of the tangent line. What the normal line is, where's my other pen? The normal line is the line that also goes through the point A, f of A, but instead it is perpendicular with the tangent line. So actually, the equation of this line would be y is equal to, y minus f of a is equal to -1 over f prime of a times x minus a. And I get that just from the fact that perpendicular lines have negative reciprocal slopes, like the line y is equal to 2x and y is equal to -1 half of an x are perpendicular because their slopes are negative reciprocals. Y is equal to -3/5 x and y is equal to 5/3 of an x are also perpendicular because their slopes are negative reciprocals. That's where I got this. -1 over f prime of a is the negative reciprocal of f prime of a. So we will, let's work an example. Let me get a new piece of paper. So we've got this line, y is equal to x square root of x. And what we want to do is we want to, first off, we're going to find tan line to y at the point, and I got to find it, lost 1, 1. And the second thing we're going to do is find normal line to that curve y at the same point. Okay, so we've got a point A, we've got a point f of A, that's our point 1, 1. So we get A is equal to 1 and f of A is equal to 2. What we need now is we need f prime of A. which, if we were to apply the limit definition, would be equal to the limit as h goes to 0 of f of a plus h minus f of a all over h, which for this problem would be the limit as h goes off to 0 of a plus h times the square root of a plus h minus a square roots of a all over h, which we could definitely do. We've solved problems like this before, but now we don't have to go through all of this to solve this problem. And I haven't worked it out, but my first attempt would be to multiply top and bottom by a plus h times the square root of a plus h plus a square roots of a. What you do on top, you have to do on bottom. A plus h times the square root of a plus h plus a square roots of a. And after you factor that whole thing out, you would be able to get to your answer. And for good measure, we could go through, we could put a 1 right there, put a 1 right there, put a 1 right there, 1 right there, 1 right there. This would simplify a bit. So there's things we could go and do in order to make this limit easier to take. But if we just use the power rule, so this is old way, kind of hard. Just a lot of algebra. As you guys have experienced by now, calculus can turn into a lot of algebra. If we take y, well, that's x times the square root of x. If we represent this as x with just an exponent, that'd be x to the 3 halves. And now y prime, which is the same as f prime of x, which is the same as the derivative with regards to x of x to the 3 halves, is equal to 3 halves. X to the 3 halves take away 1 is 1 half. All this is just trying to get you guys familiar with the fact that there's a lot of different ways to say the same thing. You don't have to write this, but when I was taking calculus, I felt kind of overwhelmed with how many different ways there were to indicate the same thing. So I'm just trying to, through repetition, show you that they're all synonyms. They're all saying the exact same thing. There's just different ways of conveying the same information. Okay, so we know that y prime of x is equal to 3 halves x to the 1 half, or f prime. So if we want f prime of 1, that's going to be equal to 3 halves of 1 to the 1 half. 1 to the 1 half is just 1. That's the square root of 1 after all. That's equal to 3 halves. So what we have is we have the point a, f of a. That's 1, 1. And we know f prime of a, that's equal to 3 halves. So, nice. This is our easier way, new way, kind of easier. So, for 1, the equation of our tangent line, the formula is y minus f of a is equal to f prime of a times x minus a. Well, that's the same thing as y minus 1 is equal to 3 halves of x minus 1, which is y minus 1 is equal to 3 halves of x minus 3 halves. You can see at this point I got committed to not fitting them both on one page. Adding 1 to both sides, y is equal to 3 halves of an x. 3 halves plus 2 halves is a negative 1 half. Do I have it back? I do. For 2, y minus f of a is equal to negative 1 over f prime of a, x minus a. Y minus 1 is equal to negative 1 over 3 halves. 3 halves. X minus 1. 1 divided by 3 halves is the same as multiplying by 2/3. Y minus 1 is equal to a negative 2/3. X minus 1. Y minus 1 is equal to negative 2/3 x plus 2/3. Y equals negative 2/3 x 2/3 plus 3/3 is a positive 5/3. So this is something that we've been doing. We did this in 2.8. We did this in 2.7. There's a formula. It's still just point slope form. Y minus y1 is equal to m times x minus x1. We've just called y1, x1, and m something different now. But this whole example, this was example 3, for those who care to know. Example 3, this was really to illustrate that we no longer have to use these limit definitions. Using the power rule will allow us to quickly take derivatives to find slopes of tangent lines, equations of tangent lines, whatever we need to do. So, the next rule we have is the constant multiple rule. And that's if we have y being equal to some constant times f of x. And we want to calculate the derivative, we want to calculate y prime. Well, y prime, which is the same as the derivative of this function, we'll go through and just start with the limit definition as h goes off to 0 of, well, that function evaluated at x plus h is c times f of x plus h minus c times f of x all over h. Now, if you look, this limit only cares about h is equal to 0. It only cares about things that have h's in them. So as far as this limit is concerned, that c has no impact on this limit. That means we can factor out these constants, and we can pull them in front of the limit. Because once again, this limit cares about h's, so c's are free to pass in and out. That's going to be equal to some constant times the limit as h goes off to 0 of f of x plus h minus f of x all over h. But if you look, that right there is just the limit definition of the derivative of f of x. So that's equal to some constant times f prime of x. And look at what we have here. We have, if y is equal to c f of x, that tells us y prime is equal to c f prime of x. Or, written differently, that says that the derivative with regards to x of some constant times a function of x is equal to that constant times f prime of x. And this is what our constant multiple rule says. It really says you can pull constants in and out of derivatives and then just take the derivative of that function. The constant multiple rule, and then general version of our power rule. Yeah, the constant multiple rule, flipping pages. The general version of the power rule, and the fact that the derivative of a constant, and I have lost where I put it. But we can use the 3 rules I've gone over today to really break apart taking derivatives of polynomial functions. I'm going to get my notes squared away, and then we're going to move on to the next example. 1 second. I am back. So we just went over d dx of some constant times a function of x is equal to, so we didn't prove it, well we kind of did, but you can pull constants out, so that's equal to c times the derivative with regards to x of f of x, which is just that constant times f prime of x. So that means the derivative with regards to x of 3x to the fourth, well that's equal to, you can think of it as 3 times the derivative with regards to x of x to the fourth, which is equal to 3 times 4x cubed, which is equal to 12x cubed. Similarly, derivative with regards to x of, I don't know, we'll choose 5x to the negative 3 is equal to 5. Derivative with regards to x of x to the negative 3, which is equal to 5 times negative 3, x to the negative 4, which is negative 15, x to the negative 4. So the same thing applies. We can, like I said, we can pull constants out. This really gets used to allow us to take the derivative of a polynomial. So if we want to take the derivative with regards to x, x to the 8 minus 3x to the 7th plus 2x to the 6th minus x to the 4th plus 3x squared minus x plus 1, that thing. In order to do that, I need to show you this, because we haven't dealt with addition or subtraction yet. So, I got ahead of myself. Let's give you the next rule. The sum and difference rule. And what that says is that the derivative with regards to x of f of x in either plus or minus g of x, well, that's going to be equal to f prime of x plus or minus g prime of x. Once again, we get this straight from the limit definition of a derivative. We know that the derivative with regards to x of f of x plus, and I'm going to go through and I'm going to do it with plus. The same thing's going to hold for subtraction. G of x is equal to the limit as h goes off to 0 of, we'll say, f of x plus h plus g of x plus h minus f of x plus g of x all over h, which is equal to the limit as h goes off to 0 of f of x plus h minus f of x all over h minus g of x plus h minus g of x all over h by distributing, oops, I didn't want to put that parenthesis. I wanted to put one here and one over here. By distributing that minus sign and regrouping, this is where we're at. Limits, we know we can break apart addition and subtraction, and that should actually be a plus sign, because that's that plus sign, and those minus signs are those minus signs. So we get the limit as h goes off to 0 of f of x plus h minus f of x all over h plus the limit as h goes off to 0 of g of x plus h minus g of x all over h, which by definition is f prime of x plus g prime of x. And, like I said, the same would hold if we did subtraction. I could go through, and if I put a minus sign there, I could put a minus sign there and a minus sign there, which would allow me to put a minus sign here, and a minus sign here, and a minus sign here. So really, this is what we're going to use. And the way I will say it is that, remember, derivatives distribute across addition and subtraction. And that gets us over here. So now, jumping back to the example I was excited about, let me copy it correctly on the back. So we wanted a derivative with regards to x, x to the 8, minus 3x7 plus 2x6 minus 3x to the 7th plus 2x to the 6th, minus x to the 4th plus 3x squared plus 3x squared minus x plus 1. So, derivatives distribute across addition and subtraction. So we can think of this as the derivative with regards to x of x to the 8 minus, I'll call it 3, derivative with regards to x of x to the 7th plus 2, derivative with regards to x of x to the 6th minus derivative with regards to x of x to the 4th plus 3, derivative with regards to x of x squared minus derivative with regards to x of x, and then I ran out of space, plus derivative with regards to x of 1. Well, derivative with regards to x of any constant is equal to 0. So, derivative with regards to x of x to the 8 is just 8x to the 7th minus 3 times 7x to the 6th plus 2 times 6x to the 5th minus 4x cubed plus 3 times 2x minus 1. Or 8x to the 7th minus 21x to the 6th plus 12x to the 5th minus 4x cubed plus 6x minus 1. You guys might not have seen, I don't think I explicitly showed you, the derivative with regards to x. Well, using our power rule, x has an exponent of 1. That's equal to 1x to the 1 minus 1, which is equal to 1 times x to the 0, which is just equal to 1 times 1, or 1. I use that here to go from here to here. You guys are free to go from there to there. So that's our derivative. We can break up polynomials at addition or subtraction. We can pull out leading coefficients, and we can attack these terms, or we can attack these one term at a time. So let's keep going. We've got 2 more examples before we come up with another rule. So example 6 says that, so find the points on the curve y is equal to x to the 4th minus 6x squared plus 4, where the tangent line is horizontal. Okay, so we're going to find points on the curve. Y is equal to x to the 4th minus 6x squared plus 4, where the tangent line is horizontal. Remember that for horizontal lines, have a slope of 0. So find where tan lines have slope of 0. That means we want to find the points where f prime of x is equal to 0. So I'll have enough space here for a derivative, but let's keep as much of this on one page as we can. So I'll just copy, we have y is equal to x to the 4th minus 6x squared plus 4. So that means y prime, the derivative, is going to be equal to, bring that power down, 4x power subtracted by 1 minus 6 times power down 2x exponent subtracted by 1 to the 1 plus the derivative of a constant is equal to 0. So we get y prime to be equal to 4x cubed minus 12x. And if we want to know where the tangent line is horizontal, that means we want to know where 4x cubed minus 12x is equal to 0. Because remember, this is slope. So if we factor out an x from both of those terms, we can call 4x. We get x squared minus 3. And x squared minus 3 can be factored to x plus the square root of 3 times x minus the square root of 3. What this tells us, the roots of this polynomial, 0 being equal to 4x times x plus the square root of 3 times x minus the square root of 3, that tells us by the zero product rule that x is equal to 0, or x is equal to the square root of 3, or x is equal to the negative square root of 3. Technically that one went with that one, and that one went with that one, but it's fine. So all we have done at this point is found the x coordinates. The x coordinates for where we have horizontal tangent lines. Now we need their y coordinates, but we were given a rule, y, that relates the values of x to the values of y. So now we want to know, and remember y with function notation, we could just call that thing f of x. We need f of 0. That's going to be equal to 0 to the 4th minus 6 times 0 squared plus 4, which equals 4. We get the point 0, 4. We're doing this because we were asked find the points on this curve. So we need the y coordinate that gets us on this curve. F of the square root of 3 is equal to the square root of 3 to the 4 minus 6 times the square root of 3 squared plus 4. Well, the square root of 3 squared is 3. Squared again is 9. Minus 6 times the square root of 3 squared is 3 plus 4, which is equal to 9 minus 18 plus 4, which is negative 9 plus 4, which is equal to negative 5. And similarly, f of negative 3, f of negative square roots of 3 is going to be equal to negative square roots of 3 to the 4th minus 6 negative square roots of 3 squared plus 4, which negative square root of 3 squared is back to a positive 3. Squared gives us 9. Minus 6 times negative square root of 3 squared is 3 plus 4, and once again that's negative 5. So we've got 3 points. We've got the point 0, 4, and we've got the points positive square root of 3, negative 5, and negative square roots of 3, negative 5. Are the only 3 points on this curve that have a horizontal tangent line. This has got a lot of elements floating around. We have this equation. Wherever we have a horizontal tangent line, we know that the derivative is equal to 0. So we took this function, we took its derivative, and we set it equal to 0. and that gave us these values of x. Now these values of x are where the horizontal tangent line is, but that doesn't give us a position in kind of two space, if you will. It just lets us know that when x is equal to this number, the equation has a horizontal tangent line. We want to figure out the point on that curve. So once we figure out these x values, we need their y values. So we take x is equal to 0, and we plugged it into the original, because we wanted the y value on this curve to get the y value when x is equal to 0. Similarly, square root of 3 plugged into the original because we want the point on the original. And lastly, negative square roots of 3 because we wanted the point on the original. These 3 points lie on the curve. Y is equal to x to the 4th minus 6x squared plus 4. Cool, so let's do another example. Example 7, the x7. So the equation of motion for a particle, s, is given by 2t cubed minus 5t squared plus 3t plus 4. So this is our position function as a function of time, and it's measured in centimeters, and t is in seconds. Find the acceleration. Find acceleration as a function of time, and find the acceleration of the particle at t equals 2. So what is its acceleration after 2 seconds? Well, we know that the acceleration of a function is equal to the derivative of the velocity of the function, which is equal to the second derivative of its position function. So we need to calculate the second derivative of the position function. So v of t, which is equal to s prime of t, is equal to, we're going to have 2 times 3t squared minus 5 times 2t to the 1 plus 3 times 1, the derivative of t is just 1, plus 0. All this is just our power rules and constant rules and breaking things up at addition and subtraction. I'm going to rewrite our velocity as a function of time is equal to 2 times 3 is 6, t squared, minus 5 times 2 is 10, t, plus 3, plus 0. So this is our velocity function. Our acceleration function, our acceleration as a function of time is equal to the change in our velocity as a function of time, or you can think of it as the change in the change of our position. Well, let's apply the power rule here. We're just taking the derivative of velocity. That's going to be equal to 6 times 2 t to the 1 minus 10 times t to the 0. So minus 10 plus 0. Or we get acceleration as a function of time being equal to 6 times 2 is 12t minus 10. So this is our function for the acceleration of the particle, whose position is given by this function. And the particle's acceleration at 2 seconds is 24 minus 10, which is 14. But now we need to have a discussion about units. Remember I said that your units come from your limit. So we know that velocity is equal to our position, and I will just call it t. We know that our velocity is given by the limit as h goes off to 0 of of s of t plus h minus s of t all over h. And remember, h is going on your horizontal axes. For this function, we have a time and we have a position. And as we're letting h go to a specific time, we care about the derivative right here, and that value of h is getting closer and closer to t from both sides. So what we have is, this thing is measured in centimeters on the y-axis and second on the x-axis. So right here we have centimeters divided by time, so velocity has a unit of centimeters per second. Down here for acceleration, acceleration as a function of time is equal to the limit as h goes off to 0 of a of t plus h minus a of t all over h, which similarly, these are v's. V's, so we have this centimeters per second divided by another second, which would give us centimeters divided by seconds squared. So our units are centimeters divided by centimeters per second squared. Next is exponential functions. We're not really going to get a good tangible rule out of this. In a couple sections we will get our good tangible rule for what we're about to do. But for now, this is really a discussion to teach us about the number e, which I've said before is about 2.7. So let's say that we have some function f of x being equal to some constant b to the x. Well, if we wanted to calculate f prime of x, that's going to be equal to the limit as h goes to 0 of f of x plus h minus f of x all to the h, which by substitution, limit h0 of b, and I've jumped from cursive b to print b, sorry, x plus h minus b to the x all over h. Gosh, we've got lawnmowers, we've got jets going by. I'm sorry for the background noise, everyone. Limit as h goes off to 0. We've got a b to the x here and a b to the x here. Let's factor those out. B to the h minus 1 all over h. And then, once again, so this b to the x doesn't have an h in it. It's just a b to the x. And this limit only cares about h. So this is kind of like a constant in the eyes of this limit. So this b to the x can be pulled out front. So we get b to the x times the limit as h goes off to 0 of b to the h minus 1 all over h. We're going to backburner that. If we wanted to calculate, say, f prime of 0, given that f of x is still b to the x, well, we're going to use the limit as h goes off to 0 of f of 0 plus h minus f of 0 all over h, which for this problem would be equal to the limit as h goes off to 0 of b to the h minus b to the 0 all over the h, or limit as h goes off to 0 of b to the h minus 1 all over h. That thing right there. So we can rewrite this as b to the x times f prime of 0. And for now, this is as good as we're going to get, that the derivative with regards to x of b to the x is equal to b to the x f prime of 0. And now we're going to have to calculate f prime of 0, this thing, for different values. So we're going through and we're going to calculate this value for different values of b. So we're going to make a chart. We're going to have an h column. We're going to have when b is equal to 2, we get a 2 to the h minus 1 over h. And when b is equal to 3, we'll get a 3 to the h minus 1 over h. And we'll do this for a couple values of h. 0.1, 0.01, 0.001, and 0.0001. That'll give us 0.7177, 0.6956, 0.6934, 0.6932, and 1.1612, 1.1047, 1.0992, 1.0987. So, as h limits to 0, we're going to say this number limits to about 0.69, and this limits to about 1.1. So, this shows us that the derivative with regards to x of 2 to the x is about 0.69 times 2 to the x, and that the derivative with regards to x of 3 to the x is about 1.1 times 3 to the x. So to calculate the slope of the tangent line to the curve, y is equal to 2 to the x, this is the equation we would use. 0.69 times 2 to the x for any value of x. Similarly for 3 to the x. So by the intermediate value theorem, because we can kind of view this as a function, we know that there has to be some number that, and let me make sure that I get to the right spot, we know that there is some number that the limit as h goes off to 0 of this number to the x minus 1 all over h has to equal 1. We know that by the intermediate value theorem. We kind of viewed this as a function, and it's continuous for all real numbers. What the book does, and what what mathematicians have done, is we have let e is equal to that number. E is the number such that the limit as h goes off to 0 of e to the x minus 1 over h is equal to 1. And what does that say? That says that the derivative with regards to x of e to the x is just going to be equal to e to the x. This is the takeaway from that discussion that I want you to have. The derivative of e to the x is equal to e to the x. We will come up with a better version of this. You might have to use it in your homework, but for now, we'll come up with a better version of this in a section or two. We don't yet have the techniques developed needed to actually do this. But the derivative of e to the x is just e to the x. That means that if f of x is equal to e to the x minus x, well, f prime of x is going to be equal to e to the x, because the derivative of e to the x is e to the x, minus the derivative of x is just 1. F double prime of x is equal to e to the x minus the derivative of a constant is 0, or just e to the x. F triple prime of x is just the derivative of e to the x, and the fourth derivative of f is just equal to e to the x. Derivative of e to the x is equal to e to the x. Derivative of x is 1, derivative of constant is 0. This was to illustrate a point. And so, our final example so, at what point on the curve, and I'm sorry about that lawnmower, at what point on the curve y is equal to e to the x is parallel to the line y is equal to 2x. Cool. So we've got a couple things floating around here. Really the only thing we need off of this page is that the derivative with e to the x is equal to e to the x. That'll give me some elbow room. So, dissecting this problem. At what point on this curve, okay, we need that, is parallel to that line? Well, we know parallel lines have same slope. So we need the same slope as this line, which is 2. So at what point on the curve y is equal to e of x is parallel to the line y is equal to 2x is another way of saying where on the curve y is equal to e to the x has a slope of 2. And how do we find the slope of a curve? Well, that means we want to figure out where the derivative with regards to x of e to the x is equal to 2. Well, the derivative of e to the x is just e to the x, and that has to equal 2. And now to get at the x and the exponent, you guys need to use a natural log. That means, well, you could use any log. If you use a natural log, the e will cancel. That means the natural log of e to the x is equal to the natural log of 2, which by definition means that x is equal to the natural log of 2. So once again, we have found the x-coordinate on this curve that has a slope of 2. Now we need to find the y-coordinate. We were provided a rule that allows us to convert from x's to y's. So we know that y has to be equal to e to the natural log of 2. Natural log of 2, I believe, is about 1.4 if I remember correctly. I know this, no, that's the square root of 2. I don't have the natural log of 2 memorized. For what we're doing, I would always encourage you to leave your answer as e to the natural log of 2, which actually just simplifies down to 2. There we go. So, natural log of 2, this is what I want to talk about. You can leave your answers in exact form. Whatever decimal expansion you use for natural log of 2 is just an approximation. You can leave your answers as the natural log of 2. And in fact, this is greatly preferred. Okay, so typically in my calculus class, this would be greatly preferred. I'm going to have you guys enter your answers numerically, and I'll tell you how many decimal places to expand this to. But typically in my calculus class, I would say this is the preferred version of your answer. So for homework, most of your homework is just calculate derivatives. 3 through 31 every other odd, 33, 35, 55, and 65. If you guys are struggling, You can do the other half of those odds. It's just a big long list of derivatives. I would highly recommend them. This can be kind of a lot of work by itself, so I didn't want to assign all of that and drown you guys. You guys have a test that you'll be working on. This isn't due for a week. This will be due next Friday. I believe next Friday is the 12th. I will have to double check that. I believe it's the 12th. But due next Friday. Let me know if you guys have any questions. Send me an email, and I'll talk to you next time. Bye-bye.